Hello everyone. In the previous lectures, we derived the basic equation to describe the evolution of an accretion disk. First of all, we'd like to estimate the time scale for viscous accretions. The basic equation for the evolution of the surface density of a disk is given by these equations. We'll show this equation is a diffusion equation later. Use the order of magnitude to estimate the time scale for the diffusions. We'll find the time scale for viscous evolution of a disk. The first term in the left-hand side is expressed sigma divided by tau accretion. This is the accretion time scale. And the second term, derivative is expressed 1 over r. Second term is expressed sigma nu over r squares. So these two terms have to be equal. And the sigma cancel in the both sides of the equations. Then you could estimate tau accretion is expressed r squared over nu. This is the time scale for viscous accretions. So we need to find out the kinematic viscosity of nu. The kinematic viscosity can be calculated by the product of the sound speed and the mean free path when collisions between the gas molecules are the source of viscosities. Then you can substitute nu to the viscous accretion timescale. Then we could estimate 10 to 14th years. This is much longer than the age of the universe. So kinematic viscosity nu need to be larger than the molecular viscosities. We need the anomalous viscosities. We introduce the alpha models for the huge viscosities. In the alpha model, turbulence is responsible for the anomalous viscosities. We consider a number of vortices in a disk. Instead of the mean free path of gas molecules, we use the scale height of a disk to calculate the kinematic viscosities. So in the case of the molecular viscosity, nu is expressed the product of the sound velocity and the mean free path. In the alpha model, alpha viscosity is expressed nu equals the alpha times c the sound velocity times h. H is the scale height of a disk. So compared with the mean free path, scale height is much larger. Scale height is 50 billion times larger than the mean free path. We introduce the parameter of alpha to adjust turbulence intensity. Then we could estimate the accretion time scale gonna be 200,000 years when the alpha is equal to 0.01. So we use the alpha model to discuss the evolution of an accretion disk. So mass flux can be calculated using the equation of motion in theta directions. Sigma r v sub r is expressed this equation. Then if you substitute omega is a square root gm sub star over r cubed, you could calculate the m dot is equal to the minus 3 pi times sigma nu plus 2r times the partial derivative of sigma nu with respect to r. So mass flux through the circumference of a disk need to be constant. Protostar is located at the centers. So mass flux through the inner radius or outer radius, same mass flux. Then mass cannot be accumulated at some specific radius. So mass flux need to be constant throughout the disk. So this means a partial derivative of the sigma nu with respect to r have to be 0. Actually, we'd like to estimate the nu is a kinematic viscosity using the alpha model, alpha ch. H is expressed c over omega. Then you can substitute alpha c squared over omega. And the c squared is proportional to the temperature of a disk. Is proportional to the r to the minus 1 over 2. In the outer region, temperature is decreasing. We'll show this later. And the omega is r to the minus 3 over 2. Nu is proportional to r. Then nu times sigma have to be the constant. It's independent of r. Then we could find out r dependence of sigma. Sigma is proportional to the 1 over r. So we could find out the steady state surface densities using the simple order of estimate analysis. Then practice 3.2. Derive the diffusion equations from the basic equations for the evolution of a protoplanetary disk. So G is expressed 3 pi sigma r square nu omega. So from this equation, sigma nu is expressed G over 3 pi r square omega. So we use the omega and the r square omega. You can express the sigma nu r to the 1 over 2 is expressed G 3 pi square root gm. And also J is expressed square root gmr. So from these equations, 1 over r is expressed gm over j squares. Then we'd like to change the partial derivative with respect to r to the j. So round r is expressed, use the chain rule. Round j, round r, round j. Then we could calculate this is equal to the 1 over 2 square root gm over r. It becomes 1 over 2 j over r round j. Then we'd like to change the basic equation for the evolution of the protoplanetary disk. We multiplied 3 pi r square nu omega in the both sides of the equations. Then it becomes g over 3 pi square root gm. This is gonna be round g round t. R to be converted, use the 2. So it becomes minus 3 over 2 nu omega j round j to the 1 over 2 round j equals 0. Then it becomes the omega j is a square root gm over r cube times gmr. So this is gonna be gm over r. The equation becomes, this is kappa. Then we have a diffusion equations. Then we'd like to find out the steady state solutions. In the steady state solutions, round t have to be equal to the 0. Then we have only the second terms. So to satisfy these equations, inside of these quantities have to be the constant value, c sub 1s. Then you could integrate in the both sides of the equations. Sigma nu square root r equal 2 over 3 c sub 1 r to the 1 over 2 plus integration constant c sub 2. Then divided by the square root r in the both sides. Sigma nu is expressed 2 over 3 c sub 1 plus c sub 2 r to the minus 1 over 2. So we consider the constant mass flux independent of radius of r. So to satisfy this condition, c sub 2 need to be the 0. So sigma nu is expressed as 2 over 3 c sub 1s. Then we introduce a new variable of the capital C. So sigma nu is expressed as c over 3 pi. Nu is proportional to the r. So nu is expressed nu sub d and r over rd. Nu sub d is a kinematic viscosity at r equal r sub d. Sigma nu equals c over 3 pi. So from these equations, sigma is expressed c over 3 pi nu sub d r over r sub d. Then we'd like to calculate total mass of the disk. Then you can substitute this sigma is here. It becomes, so this is go to the infinities. We find out the disk diverges when the nu is proportional to the r. We multiply a factor to decrease the density. We multiply the exponential term with a power law density distributions, where the r sub d is the size of a disk at t equals 0. Then we could calculate the total mass at t equals 0. Then if you perform the integral, this is the total mass of a disk at t equals 0. So from this equation, you can find the integration constant of the c. Then sigma at t equals 0 is going to be m sub 0 over 2 pi r sub d r exponential term minus r over r sub d. So this is the surface densities at t equals 0. Then we'd like to solve this diffusion equation as the initial conditions. G, j, t equals 0 is expressed fj. The Fourier transform in the both sides of the equations. So Fourier transform, the G becomes a function of the alpha and the T. The inverse Fourier transform, so this becomes G as a function of J and T. Then this equation becomes, then this ordinary differential equation is quite easy to solve. So instead of the C, we could use a G alpha 0 exponential minus kappa alpha squared T. To find the G alpha 0, you could perform the Fourier transform. So inverse Fourier transform. And also inverse of the exponential minus kappa T alpha squared. It becomes 1 over 2 square root pi kappa T exponential minus J squared over 4 kappa T. So from this equation, you can find the G using the inverse Fourier transform of the G alpha T, or G alpha 0 exponential minus kappa alpha squared T. So we use a convolution theorems. Then this equation is expressed. So I showed general solution can be expressed this equation for the diffusion equation. Then we need to substitute the initial condition for the G. G is expressed 3 pi sigma r square nu omega. So G J T equals 0, 3 pi sigma r T equals 0, r squares nu omega. Then you can substitute nu equal nu sub d r over r sub t. And the J is a square root gmr. J sub d is a square root gm r sub d. The equation becomes, so we could express the initial conditions for the G. Then G Jt is calculated. Then we perform this integrals. And I showed just only the final solutions. 3 m sub 0 u sub d over 2rd squares times j normalized times t tilde. Power index is a minus 3 over 2 exponential minus j over j sub d squares over t tilde. The t tilde is expressed. This is equal to t over t diffusion time scale plus 1. So we use a Fourier transform to find out the solutions of the diffusion equations. Then we convert from the G to the sigma. Surface density is expressed this equation. This is surface density of a disk at the t equals 0 and the t equals 1 diffusion times, t equals 10 diffusion times, t equals 100 diffusion times. Initial surface density profile is given by the blue curves. The surface density decreases with time because the gas is accreted on protostars and some gas moves outwards, taking the angular momentum. The disk is expanding with time. The red ones t equals 100 diffusion time scale. The disk is significantly expanding, and also the magnitude of the surface density is decreasing. In the comparison with the observations, a disk expands because some gas molecules gain the angular momentum and move outward. So horizontal lines show the age of a disk. The vertical line is the radius of a disk. So radius of the disk is a followed curve given by the alpha equals 0.01. From this comparison with the observations, the good value to approximate this accretion disk, we should use alpha equals 0.01. And also we could find that the disk mass. Disk mass decreases with time because the gas migrates toward the protostars. By plotting the mass of the disk, we can estimate the initial mass of the disk. So from these figures, initial mass of a disk range 0.01 solar mass to the 0.2 solar mass. In these lectures, I explained the accretion disk and the basic equation for the evolution of accretion disk. By transfer angular momentum outward, majority of the mass is migrating toward the central stars and losing the surface density of a disk. So we can explain observational result if we use alpha equals 0.01 and the initial mass of the disk is in the range of the 0.01 to the 0.2 solar mass. Okay, this is the end of this lecture.